Sverrisdóttir, and her topic will be Eigenvector Varieties.
Thank you, and thank you for having me here. I will be speaking about the project that's very recent with my former advisor, Bert, and my current advisor, Sandra. And we can just start with what we would guess from the name of the talk. We start with the eigenvalue problem to solve this equation here. Now, but I think this is a very general question. We've seen this in linear algebra a long time ago. We know that the matrix may be static and non-visible. Then we have using eigenvectors and so on. So I'm gonna start here in a bit. And I'm gonna rather think about family of matrices and look at this eigenvalue equation for this parameterized matrix. So here, T, these are variables, complex variables, and our matrix depends linearly on T. And now we solve this. So the idea behind this is in applications, matrices are very large, and you try to solve the eigenvalue problem, but it just becomes infeasible to solve them for large matrices. But often you have matrices that are very structured. So often you have matrices that linearly depend only on the variables, and this V is way less than the actual number of variables or entries in the matrix. So it is a very special structure. So the motivating question for this project is that what constraints does this special structure impose on the corresponding eigenvectors? All right. So let's make this a bit more concrete. What I mean by this. So we have a linear space of matrices, two-dimensional. So D will always be the dimension of this linear space, and we will be looking at n by n matrices. And we can either look at it as a matrix with the variables T entries are variables for linear forms in T, or we can think about it as a linear space. So we have a basis, D matrices that form the basis here. And its eigenvectors, they are algebraic functions in T. They're not necessarily rational or something like that. And I'm going to say they parameterize this eigenvector variety, denoted by EA. So I will not say that the eigenvector variety is the Sverrisdóttir closure of all possible eigenvectors of matrices in this linear space, and we'll see later why that is the case. We want to constrain it a bit more. So, okay, an example. So what do I mean by that? So, all right, so this is my parameterized matrix. Maybe some people recognize this matrix structure. These are the companion matrices transposed. They're used to solve polynomial systems using eigenvalue equations. Solve a polynomial on one variable. Okay, so this is a 5-dimensional space of 4x4 matrices. And if T1 is not equal to 0, then its eigenvectors are this form. So if you have the eigenvalue lambda, the corresponding eigenvector will be this. Right? Now, okay, I made this constraint that T1 is not equal to 0. But that's okay. Because of my definition here, I don't care about that case. So the eigenvector variety is just a twisted cubic. And this is the variety parameterized. Okay, so even more concrete, now more algebraic maybe also. So I will go back into applications later, but I want to make this definition very clear. So one way we can define this variety as well is we start with just the incidence here. So we have T, it can be any complex vector here, except maybe not the 0 vector. Then we look at all T's, the corresponding eigenvalue and an eigenvector. And this is a variety and full disclosure. So this is a variety in the space here. Now this variety can have many irreducible components. And the thing is that, so what I meant earlier is that some of these irreducible components, they may only happen for special matrices in H. So, for example, if my H here contains the identity matrix, then every vector is the eigenvector of the identity matrix. We don't want, because then if we look at the eigenvector variety, then it's contain all of those. We just can't. So that is exactly what, if we have the identity matrix in here, this we will get an extra component that will contain the identity matrix. We want to remove it. We want to remove those components. So we keep only the components that describe these relations for generic matrices, so almost all matrices. And this picture here, so we have then this J where we only take the nice components, and we can either project it down to a matrix and an eigenvalue. They will fulfill the characteristic polynomial. They will, this, I write that right here. Oh, you can see that.
Can move it for now.
Fine, so for didn't understand what I was saying. The first one is this eigenvector variety consists of all eigenvectors of generic matrices in my linear space.
More.
You can continue, Svala, then.
Okay. Okay, and then this is
No. No, I don't think I can. I'm sorry. If you could,
yeah.
this.
Okay, great. Okay, now is it clear this object that we're going to be looking at? This is the eigenvector variety of a linear family of matrices, and these are the eigenvectors that are here for generic cases of those matrices. Okay. What? Okay. So I'm gonna just there's a nice actually here you can get right away from this definition. And they come from this characteristic polynomial. So this characteristic polynomial, usually we think about it as a polynomial in the eigenvalue. You solve it, it's a degree n polynomial, but now we have these p variables. So now it's a homogeneous polynomial of degree n and d plus 1 variable. So it might not be reducible into linear factors. Usually it's not. And so we have a proposition that says each irreducible factor of this polynomial will be one-to-one correspondence with the irreducible components of our incidence variety. And then also, if there's a characteristic polynomial is square free, it has no repeated factors. This when every component has dimension d-1. And the reason why we care what's happening with this J, so J is here, this top component we project down to get the eigenvector variety, is that it gives us some upper bounds on what can happen for the eigenvector variety. So if this has dimension d-1, then this can happen. Unless dimension d-1. And then most of this is components. And an example, to go over this again, is we look at this family here. Now we have B is equal to 4. We have 4 parameters, and it's a 5 by 5 matrix. And we compute this incidence variety in Macaulay or something, and we get 4 irreducible components. One of them is defined by this idea. So if we look at this here, we say PR is 2. So we end up with 4 times P1 all on the diagonal, and then we set these to 0. So we get a scalar matrix. That's a probable component because every vector is an eigenvector of a scalar matrix. So this is exactly what we want to get rid of. And then we have other 3 irreducible components. This corresponds to 3 irreducible factors, the characteristic polynomial. So this characteristic polynomial has no repeated factors, so the incidence variety here has dimension three components. And actually, the eigenvector variety the dimension will drop by one even further. So we'll have dimension two, and it will only have two pairs. And this actually matrix traveling will appear later in the applications. So we'll see this later. Okay. So the thing we should always look at is what happens generically. So what if I just take random matrices here and I create a three-dimensional linear space of matrices? What will my eigenvector variety be? Okay, now we can say everything. We know everything about this. First of all, the variety is cut out by the p plus 1 by p plus 1 minus of this matrix here. So this is p plus 1 by n matrix. And this is very natural why this is true. Because to be eigenvector, you want x to be in a kernel here. You want the x to be a linear combination of these two distances versus the t's. So this is very natural, and this before it doesn't matter in the generic case, our eigenvector variety will always fulfill these equations, but we might need more. And this we get a proper variety when the dimension of the linear space of matrices is less than the size of the matrices. Then we get its dimension is p minus 1, and its degree is n choose p. So, and this will be irreducible except for this single interest, because then we will just get n eigenvectors. And this actually comes from a very known theory formula for enclosed set. Here we have determinantal variety. So, like one thing that's you can take from this theorem is that, for example, say we have two matrices, H1 and H2, and we know they're eigenvectors. We know very well that their eigenvectors of their sum are not going to be the sum of the eigenvectors unless they're simultaneously divisible. What we know now is that, okay, if we have two matrices, the eigenvector variety will be a curve, and it's a curve with degree n choose 2. So it's an eigenvector of the sum will lie on a curve of degree n choose 2. So the nonlinearity here is choose 2. Okay. Now from generic to very special. So a lot of linear families of matrices are Lie algebras. When we have Lie algebras, we can describe the eigenvector variety very well. So here, if we have a reductive, the matrix Lie algebra with weight spaces VA, so we take the representation here, and we take the irreducible inclusion. We can get its eigenvector variety is the union of the closure of all G orbits of these spaces. And if this representation is especially nice, so it's minuscule, then we only end up having to use one of the orbits and make a closure. So, for example, this case is the skew symmetric matrices. This is some on the algebra 2R. And it's a minuscule representation, so we just have to find highest weight vector here, which I choose to be this, and then the eigenvector variety is Lie group. So this is also Lie group of the algebra, so we have the Lie group SON. We take its orbit here, and we get the isotropic cubic. And this is known that the non-zero eigenvectors for non-zero eigenvalues of skew symmetric matrices, they're not real. They're complex. Being on the isotropic cubic, no real constant. Okay. Another example here of Lie algebras is a bit this is just a sub-algebra of PL. So we're going to look at more of the rest. We're going to look at these additive compound matrices, and these will be important later also for, these will appear in the application. So if we now consider M by M matrix, it's defined like the matrix of this of a linear map. So G is just an element of G of M. Now we can define action on the wedge product, and this is just on this is just the induced action on the wedge product. The natural action here, so we take M(k) by M choose K matrix, defined by this linear map here. Okay, so what are its eigenvalues and eigenvectors? Okay. Okay, so the eigenvector, that's more questions I'm asking here. So this is actually a minuscule GLN representation. And so the eigenvector variety is just the orbit of the GLN orbit of this highest weight vector here. So this is some representation theory. So we can get to answer all these questions just with some nice representation theory. And so the eigenvector variety is the Grassmannian additive compound matrix. So the eigenvectors, so if the eigenvectors of G are U1 up to UN, and the eigenvalues are lambda 1 to lambda n, then the eigenvectors are wedge products of the eigenvectors of G, and the eigenvalues are just sums of the eigenvalues, the small matrix. Do you know anything about the eigenvalues and eigenvectors of the large matrix? Just from the small matrix. No. In my PhD, I did some cases in algebraic geometry for quantum chemistry. So we're gonna use this for that. So now we have K is the number of electrons in some electronic system, and M is the number of orbitals. And so the number space with the orbitals is this much more. And for reference, the Grassmannian now is the Grassmannian is the variety of decomposable species. So sometimes I think these are called separable in chemistry, even though they're not rank 1 tensor, they're rank 1 use metric tensors. And what would the operators in here are written in second compensation like this. Okay, for people haven't seen this, they're actually just the K additive compound matrix of the transition matrix H. Okay, so that's why I went over this additive compound matrix example before this. Okay, now they are additive compound matrices, but we can't take any matrix. We're going to take only Hermitian matrices. We no longer have Lie algebra because Hermitian property or even symmetric property, which is that Hermitian is symmetric. I wouldn't have something that is a Lie algebra. But still, this theorem here, it doesn't only hold for the algebras. It holds for much more things. And it actually holds here. So actually the eigenvector variety of one-body operators is now you take the unitary group Hermitian and the highest weight vectors, and this is still the Grassmannian. So the eigenvectors of one-body operators is lie on the Grassmannian. They're separable. This is known, but now we have the other direction of that we can actually get every Grassmannian. Every element in the Grassmannian from one-body operators. And now for the bosonic case, we do this very analogously. So now I will work with this metric K symmetric power, CPN. I assume the number of bosons is K and N is the number of sites. I think often people work with this computational number space, but I will work here to make this work out, but there's a very nice projection between these two and the same rule. So the analogous object to Grassmannians here is Chow varieties. And these are just decomposable symmetric tensors. So here, an example of a Chow variety, they're all indexed by coefficients, is when they're all different. And usually here, we index them by lambda, and they will, and that records the occupational number. So I think so the analogous theorem here for bosonic states is the bosonic one-body operator has the bond eigenvector. Is the Chow variety. Now, a corollary of this is that the bosonic one-body operators have a separable ground state. So the Chow variety for lambda just I want to K here. This is just a very nice set. And actually, ground states will always lie on this component. So I think this is also known, but I think this is known yeah. One-body operators are very well understood, so we're going to two-body operators. And we have a theorem here. We know that the eigenvector variety of two-body operators is irreducible variety. It's a proper subvariety when K is less than 7 and L is less than 15. And then we know its dimension is the following. All right. We conjecture that it's not just a upper bound, that this is an equality. And with that, we show why we can make this conjecture, and this is done by numerical computations. This is a very large number, 7, 15, like 3,000 something. But we can numerically verify the dimension of this variety for large cases, and we get here. And this is P is this number here. Here, so we want this to be 2 less than this column. Very well.
With that, are there any questions? And maybe inside the bounds that we have to slightly before.
This one here.
Yeah, the dimension of variety that we can
Yes.
find like an analytical result for this. And I mean, this is now still for K larger equal to 7 and larger equal to 15.
Yes. Okay, less than equal to 7 and less than 15. There will be no constraints on the eigenvectors, actually. So there's nothing starts to happen until this case. And this bound here is the general bound, and then we subtract one more because we have the identity matrix in there. This will make that. So, is that your question?
Yeah. So this will be then, if I know that I have, for example, a fermionic system, a fermionic combinatorial, up to 2-body operators, then this is sort of the number of possible non-degenerate states that I can.
It's a dimension. So
the
number of parameters needed to construct eigenvectors of 2-body Hamiltonians. Yes. Yeah. So kind of. Well, this is not necessarily a parameterized variety, so it's not that easy. But the number of free parameters in these for these eigenvectors is.
You would find the parameterization.
Yes.
And this would be the number.
Yes. Exactly.
I have a very different question. Do you know anything of what happens to this variety when you take tensor products as in Aristotle, for instance? You take tensor product of linear spaces in this way, and you make the matrix bigger.
Oh yes.
And,
you should get regular products of the eigenvector variety should be products of should be the regular products of the eigenvector varieties of the other two. So to get for example, the Segre variety, you could do this. Yes.
Yeah. We have time for one more question.
You know, one question, but the matrices are